So we have been exploring the idea that an electric field and a magnetic field that vary with time propagate through space as waves, and we've been relating it to light. Well, now we want to actually show that what we derived before actually propagates through space, and we're going to do that by using the wave equation. So if a function that describes a wave, so this is your wave function in here, satisfies the wave equation, we know it actually propagates through a space. So wave function must satisfy the wave equation, so this side must equal this side using your wave function in order for the wave to propagate. So we're going to go back to Faraday's law and Ampere's law in order to be able to do this. With Faraday's law, so once again we have our y direction or x direction. The electric field is in the positive y. The magnetic field is in the positive z direction. And I've once again drawn my box here, the dl that we're going to integrate over. And mind you, these should extend through the box. So the box should actually be around these, but I was trying to draw a diagram that could easily see everything. So one side of the box is A, the other side of the box is delta x. So we have Faraday's law. So I've written the integral of E dot dl half here. So the integral of E dot dl is going to equal the electric field in the y direction times the side A plus the electric field in the y direction as we've now stepped the wave forward. So x plus delta x at some other time t times A, because the length of this box is not changing. We're then going to look at the other half of Faraday's law. The fact of the flux is changing with time. So we're going to take the partial derivative, because now instead of just looking at the idea that the electric field is going to vary with position, we're going to talk about the electric field varying with time. So we're going to take the partial derivative, because it's a function of two different variables as you saw up here in terms of t, and then for the area we're going to use A and delta x to represent the area of the box that the magnetic field is going through. And remember, this magnetic field is just not here, it's actually coming out of the page the whole way through everything. And then I'm going to equate them. So the a's here cancel out. Notice I remember the minus sign this time. And then I'm going to remove delta x to the other side. Now this shift forward that we're seeing here, the idea that we're looking at what the electric field does at some forward position minus some past position, that's the same thing as taking the partial derivative in terms of x. So I've moved this delta x over to the other side and I turn it into a partial derivative so that we take this relationship here. And then I'm going to take the partial derivative again in terms of x. So this turns into the second partial derivative in terms of x. And then we have down here the partial derivative in terms of t and the partial derivative in terms of x. We're now going to skip up here. We'll come back to this in a second. And we're going to apply Ampere's law. So we have the integral of B dot dl, which is, once again, the electric field is out of the page now because I've rotated the coordinate system. And the B is still in the z direction, but I've rotated the coordinate system so it looks like it's in the minus y. And once again we have our box, and remember the electric field is coming through the box, the magnetic field is going down through the rectangle here. And we have sides A and delta x. So we have the magnetic field at one position, and then we have a magnetic field at a different position. And we multiplied by A because, once again, that's the only side of our rectangle here that is parallel to the magnetic field. We then get the electric flux by doing the same thing. So area here is going to be A, which is this side of the box, and delta x, which is that side. And then I'm going to divide by the partial derivative to turn it into the change in electric flux with respect to time. And then I'm going to set the two halves equal to each other, and I want to make sure that I include the constants. So the A's cancel out, and once again I'm moving the delta X to the other side so that this step forward in position gets taken care of by the partial derivative. And then I'm going to take the partial derivative in terms of t to both sides this time, so this becomes the second partial derivative, and this becomes the partial derivative in terms of x times the partial derivative in terms of t. Notice here that this and this are equal to each other. So I've set this equal to this, which is what I've written here. And you'll notice this here matches this, where you have the second partial derivative in terms of x with the equation that would describe how the electric field propagates from time. And the other half is the second partial derivative in terms of t of the function that would describe how the electric field is going to propagate through time and space. We're just left with these constants out front, and from a prior video, we know that this is equal to 1 over the speed of light squared, or the 1 over the velocity squared. So we've showed that at least the electric field propagates through space because it does satisfy the wave equation. And back here, if I made a different decision, here if I took the partial derivative in terms of t, here if I took the partial derivative in terms of x, I would end up with a slightly different relationship and find that the magnetic field also satisfies the wave equation. Alright, so now that we've established that the electric field and magnetic field propagate through space successfully as waves, we're going to talk about, we're going to assume sinusoidal waves because we're familiar with that shape of wave and it's not too bad for us to deal with. So we would have learned in 151 that y of x of t is equal to an amplitude times the cosine of the wave number times x minus the angular frequency times time. Alright, so a couple of things to point out here. This minus sign in the middle means the wave is propagating in the positive x direction. So you have to keep that in mind. The wave number is equal to 2 pi over the wavelength, so this is wave number. This is wavelength. And we already know that the angular frequency is equal to 2 pi times the frequency. So that's an equation we already reintroduced earlier. We also know that the speed of light is equal to frequency times wavelength. And we also know that the electric field max, so the amplitude of the electric field, is equal to the speed of light times the amplitude or maximum magnetic field. So translating this relationship here for the electric field and the magnetic field, we get that the electric field is equal to, and for this diagram it's in the y-hat direction, but it may not always be in the y-hat direction, the maximum electric field times the cosine of the wave number times x minus the angular frequency times time. Now keep in mind, this tells you the direction that the electric field is pointing. The x here and the x here tell you the direction that the wave is propagating. And the negative sign, as I said here, indicates positive direction. If it was positive here, it would be propagating in the negative direction. So the way you get this x and this y is using the right-hand rule that we discussed in the prior video. The magnetic field that's going to propagate in the x and y. And remember, the electric field and the magnetic field always have to be perpendicular to each other, and that they both have to be perpendicular to the propagation of the wave. Which means that this, and this should never match each other. And we're only going to deal with waves that are in phase with each other, which means that for both the electric field and the magnetic field, this and this are going to be exactly identical to each other.